Swayam Prabha. Digital India. Educated India.
In this lecture, we are going to discuss the impulse momentum form of the Newton's second law. This is also known as the impulse momentum relation. This relation is an integral of the Newton's second law, just like the work energy relation or work energy form of Newton's second law. This is an integral of the Newton's second law. Therefore, it is called the impulse momentum form of Newton's second law. And because it is an integral of Newton's second law, it will not generate any new information which is not already present in Newton's second law. This relation will lead us to the concept of conservation of linear momentum. Let us start by looking at Newton's second law. The rate of change of linear momentum is equal to the force. This is what is Newton's second law. Here I am using the notation capital G vector as the linear momentum vector. G is therefore equal to mass times the velocity vector. Therefore, the linear momentum vector is in the direction of the velocity vector, mass being a scalar quantity. Imagine a particle under the action of forces. The resultant force is F, indicated by this red arrow in the figure, is moving on a path from A to B. At position A, the linear momentum G at A is mass times velocity vector at A. Similarly, at B, the linear momentum G B is mass times the velocity at B. If I integrate the Newton's second law in the form that I have written, the integral from A to B of dg is equal to integral of the force over time f dt. The time flows as Ta to Tb. Ta is the time when the particle was at A and Tb is the time when the particle was at B. Therefore, I can write this integral in this form. Left hand side is a total derivative. Therefore, I can write the change of linear momentum G at B, the linear momentum at B minus the linear momentum at A, at location A. So, this is the left hand side. What is the left hand side? Let us look at this figure. As I mentioned that this is the linear momentum at A, this is the linear momentum at B. Therefore, when I compare these two vectors, I have taken these two vectors here G A and G B, and I take the difference G B minus G A. That red vector is the difference vector, and what is the difference vector? From our relation is the integral over time from T A to T B of the force vector, and that is what I have indicated there in the figure. Therefore, the change of linear momentum is equal to this vector, which is the integral of the force over time as the particle moves from A to B. The left hand side of this relation is the change in linear momentum, and the right hand side is known as the impulse of the force. This integral of force over time is called the impulse of a force. This is a vector quantity. This relation is known as the impulse momentum form of Newton's second law or impulse momentum relation. As you can very easily notice, this is an integral of the Newton's second law, direct time integral of Newton's second law, and this gives us a vector relation. Remember that impulse is a vector quantity and that impulse is the change of linear momentum. Change of linear momentum of a particle is equal to the impulse of the force acting. This is the relation, I have rewritten it. Now, imagine that this vector, force vector has 3 components f x, f y, f z in Cartesian coordinates, let us say, and because the impulse is a vector, the impulse is a vector because force is a vector and time is of course a scalar. Therefore, I can write down the 3 components of the change in momentum and the impulse of the force x, y, z. These 3 relations I obtain, these are 3 equations. Let us focus on the first part, the x direction. On the right hand side, I have a figure of a force, I have a figure of this force acting in the x direction, and I am integrating this force from T A to T B. Let us consider the situation what happens when T B slowly tends to T A. The integral is nothing but the area under the force curve, force time curve. Impulse is therefore the integral of the force time curve, is the area under the force time curve, force versus time. That area under this curve is the impulse. Now, what happens when T B tends to T A? Limit T B tends to T A of this integral, for the force shown, what happens? This area goes to 0. As T B tends to T A, the area goes to 0, therefore, the impulse goes to 0. Therefore, as T B tends to T A, there is no change in momentum in the x direction. But this is 0 only when the forces are smooth. There are examples of forces which will not go to 0 even when T B tends to T A. Such forces are called impulsive forces. Impulsive forces are forces whose integral under the force time curve does not go to 0 at certain instants. For example, here I have taken an example or this relation, I have written this relation when 2 kinds of forces are acting, smooth forces F s and impulsive forces F I. Smooth force is shown by this red curve, whereas the impulsive force is shown by the purple curve. As you can see, the impulsive force acts for a very short time at a location. Suppose it acts at T A. Then I can imagine that this impulsive force exists during the time interval T A minus epsilon to T A plus epsilon. Epsilon is a very small quantity. Of course, limit does not mean it goes to 0, but it tends to 0. Now, what are the situations where such kind of forces, impulsive forces occur? 2 common examples are collision and explosion. In a collision, for example, a cricket ball is hit by a bat. The contact between the ball and the bat is very small, or a hockey a ball or a hockey puck with the hockey stick. The time of contact is very short, but that can change the momentum of the ball or the puck. Similarly, explosion, you have very short lived forces which are very high. I mean, the force magnitude is extremely high, but acting for a very short time. Such forces are called impulsive forces, and the integral under these impulsive forces exists only for that around that time at which this impulsive force acts. Therefore, when I take T B tend to T A, or in this case epsilon tends to 0, whatever I have shown here, epsilon is the small time to the left and to the right. So, is a small time, and T A plus epsilon is to the right and T A minus epsilon is to the left, and when I do this integration over this very short time interval, then only I get the effect of this impulsive force. And in this small time interval, the smooth forces hardly make any difference. So, their contribution to the impulse is 0, nearly 0 or negligibly so, compared to the impulsive force contribution. Therefore, the short time momentum change is given only by the impulsive forces. The short time momentum change from T A minus to T A plus, where T A is the time at which the impulsive force has acted. So, T A minus to T A plus integral of f I dt is something finite, whereas over the same time interval the contribution of the smooth force is almost 0, is negligible compared to what the impulsive force can contribute. Therefore, the change in momentum of the particle will come only from the impulsive force. The smooth forces do not contribute appreciably, but remember, over this very short time interval. Let us try to understand this thing with this example of a mass falling on top of a mass spring dashpot system in a uniform gravitational field. The mass m1 has been dropped from some height. I am measuring the coordinates all positive upwards, y1 is for m1 and y2 is for m2. Let us write down the equations of motion. When this mass m1 impacts m2, at that instant an impulsive force will act on m1 as well as m2. On m1 it is directed upwards, therefore, on the right hand side I write it as plus Fi, impulsive force at the point of impact. Therefore, m1 y1 double dot is equal to minus mg, which is vertically downwards, plus Fi, impulsive force which is vertically upwards. The equation of motion for the second mass point m2 y2 double dot is equal to the weight minus m2g minus k y2, because if it goes up by y2, this spring is going to pull it back, minus k y2. If it has a velocity upwards y2 dot, then the viscous dashpot will pull it back with a force minus c y2 dot. These are all forces on the right hand side for this mass. This is Newton's second law, straightforward, and you have by Newton's third law a minus Fi acting on the mass point 2. This, in writing this, I have used Newton's third law. Now, let us try to look at the impulse momentum form for the very short duration, which is say the time of impact is t, then if t plus means just after impact and T minus is just before impact, then for the first mass I can integrate over time, and if I do that, I integrate over time this full equation, the left hand side becomes m1 constant, integral of y1 double dot is y1 dot t plus, this is being integrated from t minus to t plus, where t is the time instant at which this impact has taken place. I am integrating because outside this interval this Fi is 0, remember, outside this time interval Fi is 0. Therefore, t minus to t plus, I integrate the first equation, and what I obtain is m1 y1 dot, first integral of the acceleration is y1 dot at t plus minus m1 y1 dot at t minus, that is equal to integral from t minus to t plus of Fi, impulsive force. What happens to minus mg, that force, integral of that force over that very short time duration. Now, m1g is a constant force, forget about smooth, it is constant force, and as this t minus and t plus, this range is extremely small over which this impulsive force acts, the gravity, the weight of mass 1 hardly contributes to the change in its momentum. The major change comes from that impulsive force. The weight hardly changes its momentum, it is negligible compared to what the impulsive force will do. Similarly, for the second equation, if I do the same thing for the second equation, I integrate this from t minus to t plus, I obtain on the left hand side m2 velocity at t plus minus m2 velocity at t minus. These are linear momenta, remember, linear momenta of the mass 2 just after the impulse and minus p linear momentum of, or let me call it g, linear momentum of particle 2 just after the impulse minus linear momentum of particle 2 just before the impulse is equal to, of course, minus Fi impulsive force, that integral will be there. What happened to m2g? Again it is a constant force, k y2 minus k y2, that is the spring force, that is the spring force. This at the that very short duration of that impulsive force, when the impulsive force acts, that spring force, the mass will hardly be able to move, the mass m2 will hardly be able to move, therefore y2 hardly changes, therefore there will be hardly any contribution of the spring force in momentum change. That force will hardly contribute in that short duration of the action of the impulsive force. Similarly, the velocity, the mass m2 was, let us say, at 0 velocity, it was at rest, it will hardly have a time to move when that impulsive force has acted over that very short duration. It will hardly have the time to gain velocity and contribute to any change in linear momentum. Therefore, these terms m2g, ky2 and cy2 dot, they will not contribute in the change in momentum of mass 2, it is only the impulsive force which contributes. If I add these two relations, what I have just now written, then m1 v1 at t plus plus m2 v2 at t plus, I have collected the terms, I have collected these two terms here and this term here, and on the right hand side you will find that it is the integral of f I from t minus to t plus with opposite signs. So, when I add it cancels out. What this final relation tells us is the final linear momentum of the total system minus the linear momentum just before the impulsive force acted. So, final linear momentum just after the impulsive force acted minus the initial linear momentum just before the impulsive force acted is equals to 0. The difference is 0, which means the momentum, the total linear momentum of the system before and after the impulse is the same. So, the total linear momentum is conserved over a very short time duration. This you must always keep in mind. This is a very short time duration. If you allow time to flow, then the spring and the viscous damping force will start and the gravity weight will start doing work, and it will contribute to the impulse. But for this very short time duration, the mass will hardly have time to move, the spring force will hardly be able to do anything, no contribution in the impulse or no contribution in the change in momentum. Therefore, this is the conservation of total linear momentum of the system. You have to be very careful about this. It is the total linear momentum between which this impulsive force acts. You have to consider everything. Therefore, in the presence of smooth forces or constant forces, there is no contribution over this short time momentum change. The short time momentum change is 0. The short time momentum change is 0, or in other words, the linear momentum of the total system is conserved over this very short time. Therefore, conservation of linear momentum, if the net external force on a particle is 0 in a particular direction over an interval of time, this is for finite time interval, then linear momentum is conserved in that direction over the time interval. This is for a arbitrary time interval. Now, it can always happen that you choose very specific time interval and over which the area under the force time curve is 0, but that does not mean that momentum has been conserved, because it has to be arbitrary. I can arbitrarily choose my starting time and ending time, and if under arbitrary time ranges, if this does not change, then the net external force on the particle is 0. In the presence of an impulsive force between two particles, the short time total linear momentum change of the total system is 0. This we have just now discussed. Let us look at a problem. This is from the book of Merriam and Craig. The ice hockey puck, you can see on the ground, with a mass of 0.2 kilogram has a velocity of 12 meter per second before being struck by the hockey stick. After the impact, the puck moves in the new direction shown with a velocity of 18 meter per second. It has been shown in the figure. If the stick is in contact with the puck for 0.04 second, compute the magnitude of average force F exerted by the stick on the puck during contact and find the angle beta made by F in the x direction. Now, here something that has not been shown. Now, some force acts, some impulsive force acts, of course, which has changed this direction of the puck. The puck was moving towards the player and suddenly it is moving away from the player in a very short duration, and in such situations it is an impulsive force. Impulsive forces can change direction of a particle almost instantaneously. So, suppose if you see a particle initially moving in a certain direction, suddenly it changes direction, then you must know that there has been an impulsive force. it acts for very short duration and it changes the momentum. So, it rotates the linear momentum vector, which we have seen. The impulse of the force, if it can change the linear momentum vector in a very short duration, then there must have been an impulsive force. We will use this x y coordinate system and represent every vector and then apply, because you remember that impulse momentum form is a vector relation. V1, the initial velocity of the puck, is minus 12 I cap meter per second. It is in the negative x axis direction. So, minus 12 I cap. After being hit, velocity V2 is 18 is the magnitude, and the unit vector direction is cos 20 I cap plus sin 20 j cap, magnitude times direction, meter per second is the velocity vector. Now, we use the impulse momentum relation. The change in the linear momentum of the puck, which is mass times velocity vector in the second instance, minus, or after the after being hit, minus mass times velocity before the impact, must be equal to the impulse of the force. Now, we do not exactly know what is the form of the force. Some time varying force, usually these forces are very short duration and very high magnitude. But what we can always define is, since the time interval, roughly the time interval can be estimated, which is in this case it is mentioned in the problem of 0.04 second. Therefore, this time interval is 0.04 second. Over this time interval, I can estimate, or I can define some average force vector which acts on the particle some magnitude and some direction, some average force which has acted on the particle over this short time duration. I can define that. Finding out the exact form of the force is very difficult. Okay. That is what we are going to do. Therefore, this integral I am going to represent as an average force vector times the time interval. Average force vector times the time interval, it is that area under the rectangle which I drew. If I plug in the values of V2, V1 and mass of the puck, then I get this relation for the force, average force vector. So, average force vector into the time interval, this must be equal to the change in the linear momentum, now shown on the right hand side. If I divide, then force, average force is 144.6 I cap plus 30.8 j cap Newton. The magnitude of this force is 147.8 Newton. If this situation has to happen, then the magnitude of the force that has acted on the puck is 147.8 Newton. This is something like, I mean, if you want to get an estimate of this, how much is this force? This is something like 15 kg. I mean, you can imagine 15 kg hitting for 0.04 second, and that is the amount of force. So, 15 kg you can feel the force by holding a 15 kg block, and that has acted for 0.04 second, that much force to change the direction of the puck and actually impart it a higher velocity. And you can easily calculate the direction of that force, because we know the force vector, average force vector, and therefore, I can calculate this value beta. Cosine beta will be nothing but the x component of the velocity divided by the magnitude of the force. X component of the velocity is 144.6 by magnitude of the force is 147.8, turns out to be 0.978, and from here you can calculate beta as 11.9 degree. So, the force average force vector has acted at this angle. Let me summarize. We have discussed the impulse momentum form of the Newton's second law. As I have mentioned that this is a vector relation and an integral of the Newton's second law, therefore, this will not generate new information. It presents the information already there in Newton's second law in a different form, which sometimes is quite useful. And we have looked at the conservation of linear momentum, under what conditions conservation holds, conservation of linear momentum holds. Specifically, I would like to draw your attention to these impulsive forces. Under impulsive forces between two bodies, let us say, the net linear momentum of the whole system between which the impulsive force has acted, if you consider both these bodies as a system, then the linear momentum, net linear momentum of the system will not change. Therefore, linear momentum over this very short time duration is 0. The change in linear momentum over a very short time duration under impulsive loading is 0. We have looked at some applications, some problems of impact. With that, I will close this lecture.